In this video, we're going to take a quick look at how to find volumes using integrals. Our starting point for our volumes will be a basic fact of geometry that says that the volume of any cylinder is the product of the cylinder's base area and its height. Here on the screen, we have two examples of cylinders. We have a right circular cylinder here on the left. This is basically a soup can laying on its side. We can see that the circular end has a radius of r, and it has a height of h, which is in this picture represented as the horizontal length of our solid. And we know that the volume of such a cylinder from geometry is pi r squared h. The thing to realize here is that pi r squared is the area of the base of our cylinder. It's the area of our circular base. And so this formula falls into the category of base area times height. The second example we have here is a rectangular prism with length, width, and height labeled as L, W, and H respectively. And we know that the volume of a rectangular prism is length times width times height. Again, however, we can notice here that this follows our general principle because the length times the width is the area of the base of our rectangular prism. It's the area of this square over here, and then we multiply that by the height to get the entire volume. And so these are, although both different geometric solids, their volumes are computed using this very basic principle of base area times height. What we're going to do in this video is look at a arbitrary solid, not necessarily a cylinder, and want to compute its volume. And our basic idea is going to be to break it up into pieces that look a lot like cylinders and behave like cylinders, and then use this basic principle for cylinder volume to approximate the volume of a solid, and then use calculus to make that approximation an exact value. So let's take a look at the solid shown here. The first thing to observe is that this solid is not a cylinder. A cylinder is a geometric figure where all of the cross sections will be identical. So for example, if we take a soup can and we cut it at any point and we sort of turn it so that we're looking at the end, we're going to see that the end that we see is circular and is exactly the same circle as the top and bottom of the can. And that's clearly not going to be the case here. On one end of our solid, on the left side as it's oriented on the screen, the solid is going to be very small, and as we move to the right, the cross sections are going to get larger and larger. And so what we want to do with a solid like this is we want to split it up into little pieces and then find the volume of those pieces. So our first step is to identify sort of the starting and ending points on the x-axis. And we're going to call those A and B. So I've labeled those values here. A will be the leftmost point where the solid lives on the x-axis, and B will be the rightmost point where the solid lives. Once we have the endpoints labeled, our next step is to cut the solid into n slices of equal width. And here we want n to just be an arbitrary number. Eventually, we're going to want n to be very, very large, but for now, n can be whatever number we like. So for example, in this case, I could cut this solid along these lines. So we could make one slice right there. We can make another slice right here, and we can make a third slice right here. The dotted part of the lines indicate that those are the parts of the slice on the reverse side of the solid that we can't see. And so if I make these three cuts right here, what we can see is that we would be cutting our solid into 4 pieces, and each of these pieces would have an equal width. And so I'm going to give this equal width the name, since it's just a number and it's going to be the same for each of our slices. We're going to call this width dx. And don't worry about necessarily why we're calling it that. It will make sense later. but we just have to give that width a name. Well, now that we have these various slices, we can look at the volumes of each of these slices. So in my picture up here, this first slice would have volume, maybe call it V1. And this second slice would have slice V2. And this third slice would have a volume of V3. And the fourth slice would have a volume of V4. And if we add up these 4 volumes, we will get the exact volume of our original solid. You can think of this like cutting up a loaf of bread. If we know the volume of each of the slices of the loaf and we add all of those volumes together, we'll get the entire volume of the loaf. So in general, the volume of our solid is going to equal the sum of all of these volumes, so V1 plus V2 plus V3. And in general, we have n slices, not just 4, and so we want to add up to V sub n. So if we had 10 slices, we would want to add all 10 of the volumes together here. And because these sums can get very large, we do have sigma notation, which allows us to write large sums in a very compact way. So one way we might write this as it's the sum from k equals 1 to n of v sub k. So here k is our index going from 1 to n, and it's counting all of the volumes of each of our slices. Now that we've broken our solid up into several slices, our next step will be to approximate the volume of each of those slices by thinking of them as cylinders. The picture here shows a cropped image of the third slice of our solid that we were considering. So the volume of this particular slice is going to be labeled as V3 in our example. Notice that this solid, while still not cylindrical, perfectly cylindrical, it is much more similar to a cylinder than our original solid. Our original solid was very small on one end and very big on another. And this one still has the property that one of the ends is smaller than the other, but because of the height being much shorter than the original solid, this is much more cylindrical than the original one. And so an approximation using cylinders here would not be as inaccurate as it would be for the entire solid. And so what we're going to do is write that the solid or the volume of our kth cylinder, V sub k. We know it's going to be the base area of our slice multiplied by its height. Now, we don't know the base area of the slice because each slice will have a different base area. But we know that if we look at one of the particular sides, one of the bases of our cylinder, of our slice, we know that we have an area. It's some number. We just don't know what it is. And so we're going to give that just a functional name. I'm just going to call it capital A of x. And this will be the cross-sectional area function. And so it is a function that at whatever value of x we choose along the x-axis, A of x will be the cross-sectional area of our solid. So it will be the base area of our slice. Our height, though, we know is dx. We remember that each of our slices had an equal height, and we called that height dx. So the area of our slice, of our kth slice in general, v sub k, is going to be the cross-sectional area of the slice times the height of that slice, which is dx. So to put all of this together, we know that the volume of our solid is going to be the sum of the volumes of all of our individual slices. So that would be the sum from k equal 1 to n of v sub k. And we just determined that we can think of the volume of each of those slices as the cross-sectional area of that particular slice at the particular value of x that we need, multiplied by dx. Now this sum on the right-hand side might look familiar to you, at least the format of it, and that is this is an example of a Riemann sum. So this particular sum is the sum of n terms, and each term is a function value, a of x, multiplied by dx. What you might remember about Riemann sums is that if we then take the limit as the number n goes to infinity, in other words, let n get larger and larger and larger, this actually becomes a definite integral. And that's what we're going to get here. And so if we take the limit as n goes to infinity, and here we need to remember what n is representing in terms of our solid. N is just the number of slices. So if we sort of think about our situation here, if we have our solid cut into slices and we cut it into more and more and more slices, those slices will get thinner and thinner. And therefore, they become even more cylindrical, and our approximation of finding their volumes as a cylinder becomes more and more accurate. And if we actually do the calculus and apply the limit, actually compute the limit, then what we're going to get is an exact value for the area of each of those slices, and therefore an exact value for our volume. And so we're going to take the limit of this particular Riemann sum. The limit as n goes to infinity of the sum k equal 1 to n of a of x dx. And we get a definite integral from our starting point of a to our ending point of b. We picked these values back when we first identified our solid. It was the very first thing we did. And we're going to integrate the cross-sectional area function, which we just called d of x, or a of x. And so this is an expression, an integral, that gives us the volume of our solid that we started with. And so what we need to do in order to compute this volume is we need a way of computing the cross-sectional area at every value of x between a and b, which means at every point of our solid. And if we can do that, if we can find a function that gives us that area, then this integral will give us the volume of that solid. Let's take a look at a simple example where we're finding a volume using this integral. So here we want to find the volume of a pyramid that has a square base with a side length of 10 and has a height of 5. So we have our pyramid drawn here. Notice that we put the tip of it at the origin. And since it has a height of 5, that means the base of our pyramid will intersect the x-axis at x equals 5. And we also have a base side length of 10, which is labeled here. And so our volume is going to be a definite integral. Our solid is located between 0 and 5 on the x-axis, and so those are going to be our limits of integration. And the last thing that we need to do is to find the cross-sectional area at some point x between 0 and 5. And so what we can do here is just pick some value of x somewhere in this where the pyramid exists. So maybe we'll pick this value right here and look at the cross-section. And if we take a cross-section here, what we should see is that we do indeed get a square. This will happen at every point because of the square base of our pyramid. And by analyzing what's happening at the base, where we have an x value of 5 and a side length of 10 on the corresponding square, we can see that since 10 is 5 times 2, that at every cross-section at any value x, the side length of that square is going to be 2 times x. And so this blue square here is going to be a 2x by 2x square. And so the cross-sectional area, which we called A of x, will be the area of that square, which is 2x times 2x, or 2x squared, or 4x squared. And so this is going to be the area of the cross-section at any number x. And so going back to our volume formula, we have our integral from 0 to 5. We want to evaluate that at the cross-sectional area, which is 4x squared and dx. And so this integral here will give us the volume of our pyramid. And so fundamental theorem of calculus says this is 4x cubed over 3 evaluated from 0 to 5. And substituting 5 into this, we see that we are going to get 500 over 3. So our volume is exactly 500 thirds.